All right, it asked for component form. As a reminder, just simple component form means you can have positives and you can have negatives. So if you picked A, you're incorrect because component form can have positives and can have negatives. The word you're looking for to make both of them positive is find the magnitude of the horizontal and the vertical components. It says find the magnitude. This one says find the component form. So the component, just the component form, that alone means do that. If it says find the magnitude of your components, then you find the positive version of both. All right, just to be clear, that would be the wording difference in those. Make sure you know that. Don't lose dumb points on the test where you're like, I knew how to calculate it, I just took the absolute value of it and plugged it in, which loses a point. All right, questions on the bell work? All right, let's go over questions on the homework. Oh, okay. Yeah. 87. So 87 says, two prospectors are pulling on a rope attached around the neck of a donkey, ouch, that does not want to move. One prospector pulls with a force of 55 pounds and the other pulls with a force of 75 pounds. If the angle between the ropes is 25 degrees, then how much force must the donkey use in order to stay put? So the donkey has to have the exact force the men are putting against him, but in the opposite direction. So really I'm asking you, how much force are the guys exerting on that donkey's neck? So that is actually what the question is asking. So if I look at my quick drawing that I have here, I drew it with the guy that has a force of 55 on the bottom and 75 right here. And then I drew, well, the resultant, that magnitude here is going to be the force that the men are actually applying. So I drew that. Well, this is 25 degrees. That's between the two ropes. So that would make this measure right here 115 degrees. So in order to get this V, I have to use the law of cosines. Law of cosines is because it's side, angle, side. So I would just set it up as the side I want, V squared, equals the other two sides squared, 75 squared plus 55 squared, minus 2 times 75 times 55, times the cosine of 155, which results in 127 pounds. That's how much force they're applying to the donkey, so the donkey has to apply that same force backwards to stay put. Gracie.
How would it be 155 and
Oh, I'm sorry, 155. I just was talking without thinking. Because 155 plus 25 does equal our 180. I did use 155 here, though. Yeah, that should be 155. Good question. Leo, does that answer your question?
Yeah.
Okay, good. That's all our question is asking, so don't find the angles between or anything. Other questions? Just a quick reminder, there is going to be at least one of these problems on the test, so make sure you know how to do them. So don't just sit there and go, I had no idea how to do it, but I don't want to ask questions. All right, then we'll move on to today's lesson. If there's no more questions, I can't force them. Today we're going to talk about complex numbers. Now we're going to talk about one way to graph complex numbers and how to express complex numbers using trig. You're going to find out if you draw these pictures correctly and you look at the stuff, it's going to be almost identical to using vectors, because we really turn complex numbers into vectors to understand them and graph them. So a lot of what we talk about is just going to have a different name, but it's going to be the same type of material. So first of all, when we're doing any complex number, you can do it in the form A plus BI. where we call the A the real component, and we call that BI the imaginary. Well, that I is always going to be there to make it an imaginary. So that means really our real component is our A, and our imaginary component is our B. Those are the only two things you can change in a complex number. So now let's talk about graphing these on a coordinate system. So let's actually use an example, and we're going to graph 2 plus 4i. And all I want to do to graph it is I want to pull out what the real component is and what the imaginary component is and kind of take it out of that formula. So the way we're going to picture this is the point 2, 4. It's a positive 4, so you're going to do the 4. This will give me my real component, my imaginary component. Well, that just looks like an xy value, doesn't it? Just a point on a coordinate plane. Well, that's exactly what we're going to do. Except we're not going to call this our y and our x. We're going to call this our real axis. And the vertical one is going to become our imaginary or complex axis. Imaginary axis. But now it's going to work just like an xy plane, where this is our horizontal, left and right, and this is our vertical, up and down. So we're going to go 2 over on the real plane and up 4 on the imaginary plane. So that's going to be that point, 2, 4. Now with imaginary numbers, to write it, you actually do a vector without a head on it. So it's just a line going from the origin to that point. So that point right there on the imaginary and real axis, to make it imaginary, we draw the line to let us know that it's imaginary. So that is the same thing. How did I word that? I did. Or you can write this as 2 plus 4i. I like to use the points. It's just a lot easier to kind of picture what's happening. All right, let's do another example, the one that most people mess up on. And that is negative 2i. Every complex number has a real component and an imaginary component. That real component is out here. What number is way out here to make this true? Yeah, it'd be 0. Some people think it's 1 because they're used to saying, well, x has a 1 in front of it. It's not that. This can be rewritten as 0 minus 2i. So this is the same thing as 0 minus 2i. So it would be that point 0, negative 2. Note the negative. Because it's subtracting, it would be that negative 2. So we just go 0, negative 2, plot that point. I'll draw maybe a different color. Yep. There's my imaginary number. That is, we can put it as 0, negative 2, or we can write it as just negative 2i. Treat complex numbers like vectors. And the better you know vectors, the better you're going to know these. And the more you know about triangles, the easier these are going to be. And the other thing that I want to talk about in that treating complex numbers like vectors, with vectors we had magnitude. So vectors, we had magnitude. With complex, we are going to use absolute value. Magnitude and absolute value are the exact same thing. That is why when we're doing magnitudes, we always use absolute value bars. All right, the only difference is here, I'm going to say, find the absolute value of something. Same thing as magnitude. So when I say absolute value, I mean the exact same thing as magnitude. What is the length of this line? Would be called absolute value with complex numbers. As an example, we're going to find the absolute value of both of these. We're going to find the absolute value of both of these. Well, that's going to be written as that. Absolute value. All right, so what we're really doing is we're trying to find this length here. Well, if you think about this as a triangle, just like we did with vectors, we have a base of my triangle is 3, and the height is 4. This length right here is our absolute value of, let's call it r. A squared plus b squared equals c squared. So if I'm looking for the absolute value of something, you just have to take the square root of your two components. That'd be 3 squared plus 4 squared. So you can take it right from the formula. You don't even need to have it plotted. You can take it right from the formula. And that's just going to equal 4 squared, 16, is square root of 25. So at the end of the day, the absolute value of 3 plus 4i equals 5. So that means our absolute value has a formula that looks like this. The absolute value of a plus bi is just going to equal the square root of a squared plus b squared. But once again, you don't have to have it memorized. You draw the picture, you make a triangle, and you should know it's a squared plus b squared equals c squared, and you should be able to get that value every single time. All right, our next one, we have negative 2 minus I. Well, the components of that would be a negative 2, a negative 1. If I drew a picture of that, it would look something like this. Negative 2, negative 1, maybe that point right there. And with our triangle that we could draw, we'd have a base of 2 and a negative 1. Once again, it's just a squared plus b squared equals c squared. So if I was asked to do the absolute value of negative 2 negative I, that is just going to equal the square root of negative 2 squared plus negative 1 squared. Negative 2 squared is a positive 4 plus 1, so that's just going to be the square root of 5. So square root of 5 is that length there. And just a reminder, 5 is the length of that line there. Questions on that? So it's magnitude. It's magnitude, we're just calling it absolute value this time. All right, next thing, trig form of complex numbers. Trig form of complex numbers is very, very similar to what we did with component form. So first of all, we have a right triangle that we can create with any point that's a complex number on there. That a plus bi is that point that's up there. Well, it makes a right triangle. So if we include this theta into this triangle, we can talk about a and b in terms of theta. For example, if we were looking for the cosine of theta, that would equal cosine so ca adjacent over hypotenuse. That'd be a over r. Which if I multiply both sides by r, we're going to come up with a equals r times cosine of theta. Well, that's the same thing as our a component when we're dealing with vectors. That is the exact same formula to find your A component when you're dealing with vectors. The other one would deal with sine. So if I had sine theta, that would equal B over R. So B would just equal R times cosine of theta. But these are the exact same thing. Oh yeah, I should say R sine. But these are going to be same as vectors. Because that's how you found your A and your B for your vectors as well. All right, so if Z equals A plus BI is a complex number, then the trig form is going to be R times cosine theta plus I times sine theta. And that comes from the fact that our form needs to be A plus BI, but using our trig, we would have R cosine theta plus R sine theta times I, and you pull out that R out front, and you have that. So that is your your trig form of a complex number. So we're going to talk about how we can write complex numbers in terms of trig using those formulas. All right, so let's do that. We're supposed to write each complex number in trig form. So that means I need to have an R, which is our length. R is our length or our absolute value. And theta is that angle. It's that angle that we kept calculating over and over and over when we were talking about vectors. So that is just the angle of our vector. So if we have negative 2 square root of 3 plus 2y, the first thing I want to do is I want to plot it on a coordinate system. So that's going to be negative 2 square root of 3, comma, 2. And a graph of that's going to look something like, I should probably go a little bit further over. A graph of that's going to go negative first and then up 2, so it's going to be somewhere about here. We'll call that the point negative 2 square root of 3, comma 2. Which means this triangle has a height of 2, and the base is negative 2 square root of 3. First thing I'm going to do is I'm going to find this length. We're going to find this length. So let's just call that length, I guess, R. And we'll call it the absolute value of R. So the absolute value of R equals our two components squared. So that's negative 2 square root of 3 squared plus 2 squared. So that's going to leave us with, if you work all your way down, you should get R equals, it'd be 4 times 3 is 12, plus that is 7. 12 plus 4. Yeah, 16. So it'd be square root of 4. I mean, it would just be equal to 4. R equals 4. Now we need to find this angle here. That is the theta I'm looking for. But we're going to use beta to get that theta. That is our triangle measure. All right, to get beta, we would say tangent beta equals TOA, opposite over adjacent. So that's 2 over negative 2 square root of 3. So beta would equal tan inverse of negative 1 over square root of 3 don't technically need your calculator. It actually is a value we know because you could go square root of 3 times square root of 3. So that's negative square root of 3 over 3. Does anyone offhand know what the tangent of negative square root of 3 over 3 is, or wants to take a shot at it? Yeah.
150 degrees?
150? No, not quite.
No, 30 degrees.
30 degrees. Yep, it'd be negative 30 degrees. Yeah, because tan inverse only exists in quadrant 1 and 4. Yeah. So we have negative 30 degrees. Oh, yeah. You got your full answer, didn't you? So theta is going to equal that 180 minus that 30 degrees, which equals that 150 that you just said. You just did the full thing, didn't you? All right, now we have to write it in complex trig form, where we have our r value and our theta value. So we're just going to rewrite this as our r value is 4 times the cosine of 150 degrees plus I times the sine of 150 degrees. You guys go ahead and do the next one. So you just need your length and your angle. Make sure you have all your work down, especially in your notes. These are your notes. So I'd first draw a picture, and I'd also recognize that it's 3, negative 2. So that means it goes 3 on a horizontal and negative 2 on a vertical. So this is the length I'm looking for. So to find my r value, I'm going to say it equals the square root of 3 squared plus negative 2 squared, which equals the square root of 13. I'm also going to get my theta. Now, this has to be 300, past 300, right? It can't be less than 180 because that would be over here. So what I'm looking at is I'm going to find this little angle here, which is my beta. I'm going to find that value and go 360 minus that little bit. So we'd have beta equals the tan inverse of negative 2, which is my opposite, over 3. It's also my y over my x. Equals about negative 33.7. 360 minus 33.7 degrees, 326 degrees. That looks like about 326 degrees. That's why we draw the picture. Because if you did 180 minus 33.7, you'd end up in this quadrant and go, oh, that can't be right. It's got to be the 360. And so rewriting that, that'd be the square root of 13 times cosine of 326.3 plus I times sine of 326.3 degrees. I just want to be clear that these two things are equivalent, and we're going to show that right below. So this is going from complex form to trig form. Now we're going to go the other direction. We're going to go from complex numbers to that normal rectangular complex form a plus bi. So this is what we have right above. We have 4 times cosine of 150 plus I times sine of 150. There are 2 methods to do this. You pick which one you like to do the best. So method 1 is distribute. Okay, just end it. Distribute. What did I actually put? Distribute and calculate it, I guess. It is what it says. Distribute this 4 to both items. So we're going to distribute that 4 here. And here, I'm going to change the order just a little bit. So we're going to have that equals 4 times cosine of 150 degrees. Plus, I'm just going to change this to 4 times sine of 150 degrees. And I'm going to move the I to the other side so we can see what is being multiplied.
Well, cosine of 150 degrees is not only just a number that we could calculate, it's also one that's on our unit circle. Or you could take out your calculator and find the cosine of 150 degrees. Well, however you do it, you're going to come up with cosine of 150 degrees is going to be a negative square root of 3 over 2. Plus 4 times the sine of 150 is actually 1/2. Well, 4 times the negative square root of 3 over 2 is just going to equal negative 2 squared of 3. Plus 4 times 1/2 is 2i. That is my rectangular form. That is exactly what we had above. So this is our rectangular complex form, and this is our trig form.
I think it's a lot easier going this direction than backwards, because backwards you have to do all the tan inverse and stuff. So this way, it is just solve it, right? It is distribute that 4 and just solve for the stuff.
The other method, method 2, is to actually solve for a and b. And what I mean by that is if you look above right now, we can say a equals r times cosine of theta. Well, in this case, our r value is that 13, and our theta value is 326.3. So we're just going to do square root of 13 times cosine of 326.3 degrees. And we're just going to come up with a is about 3. Then we do the exact same thing for b. Remember, b is r times sine of theta, which is going to equal the square root of 13 times the sine of 326.3 degrees. So you're going to have b is going to be about negative 2 if you plug that in your calculator. Now this method requires you to remember it has to be the form a plus bi. So in this case, our a is 3. Our b is negative 2, so negative 2i, which is what we had above.
For my money, I usually do this one, because otherwise I'm separating it just to put it all back together again. But some people like this one just because they know what they know what a equals, they know what b equals, they don't have to worry about that kind of stuff. But for me, I usually just distribute and solve. So that's the good part about going from trig to rectangular, is it really is just solving. Whereas rectangular, if I start with rectangular, I have to go to trig, I have to find that length, and I have to find my theta.
All right, any questions for me? Yeah, Leo.
So like you just from trig to rectangular, which one would you say was easier? Just distributing?
For me,
I think the distributing is easier, bless you, just because it doesn't take any knowledge. It is just distribute that 4, and in your calculator do 4 times cosine, or if it's on a unit circle, just put the values of cosine. I think this method is easier, just because sometimes you have so many of these r cosines and sines going through your head, it's just like, well, why don't I just distribute and get an answer? You know, it doesn't take any more steps. So I like it because it takes a little less brain power because it's just distributing instead of going, okay, a equals r times sine, or is it cosine? You know what I'm saying?
Yeah.
I used to just teach this method, and then I would use this one to check it, And so I decided to teach you both of them because it's just nice to be able to have a nice quick one if you forgot how to do. Other questions?
All right, just a reminder, test corrections are due on